Hi, this is Hands-on Arduino. We're talking in this presentation about incremental encoders. Actually, there's so much to say, I have decided to break it up into two discussions because there is a lot to say. Incremental encoders are very useful in robotics and many different other applications. So, in talking about this then, we have a number of subjects to cover. Here is what we're going to talk about. We're going to talk about, first of all, what are the basics of inputting motion into a computer, information about motion. Second, we're going to talk about encoders, in particular incremental encoders, but also we're going to mention a little bit about absolute encoders and their basic functions. Then we're going to move on to talk about unidirectional decoding. So that is, if you're only going in one direction, how to do the decoding. Then we're going to move on to bidirectional decoding. So if you can go forward and backwards, that's actually a more complicated problem. We'll talk about bidirectional decoding. So these are the topics we're going to talk about in this presentation. In the next presentation, we're going to talk about using pin change interrupts, using assembly language, and some other things. So these are the breakdown of the topics that we're looking at. Okay, so how do we input motion into a computer? Basically, how do we get a physical position, whether it be linear or rotational, into a computer? Well, basically, we need something that will change when the thing we want to measure, moves. So if we have rotational motion we want to keep track of, then we have to use something that will measure a rotational change, or will have a rotational change. For example, a potentiometer. The resistance changes as you rotate this. If we're talking about linear along a line, then a linear potentiometer could also use it. Okay, and so these are actually analog devices, and they can be used. So generally, we're wanting to use something that's electrical, since the Arduino understands electrical things. It doesn't do so well with things like liquids. You know, if you pour liquids, it doesn't work so well. Electrical stuff, all right? So well, why don't we just use potentiometers? I mean, if those will do the trick, then why don't we just use those? Well, there are a number of reasons why to use one over another. It turns out that to use an analog signal basically requires an analog input. So often we may be limited by our number of analog inputs. The other issue is that for many potentiometers, you get maybe one full turn. You only get one rotation, and then there are stops on one side and on the other side. So you can only go so far using these kinds of potentiometers. Now, there are potentiometers called 10-turn pots, which will allow you to go more than one revolution. Okay, so it's possible that you can use one of those. But if you have a lot of motion that you want, you want to rotate many times, much more than 10, you're going to need something that can keep track of that rotation. And similarly, with potentiometers, you have a limited distance that you can go with that. So it turns out if you use an encoder, you can actually make it so that you can do longer distances. So for our purposes, we're primarily going to be talking about rotational encoders, but the same things apply to linear encoders. So when it comes to inputting motion, there's actually a number of different kinds of motion we could input. We could input position, and the common inputs for those are either encoders or potentiometers. Okay, so that's position information. We can input velocity information. So and for that, if we have rotational things, we can use a tachometer. Otherwise, we can use something called a rate gyro. These rate gyros can be used for obtaining velocity information. Or we can use something called an estimator. An estimator would, for example, take the position information and use it to estimate velocity. Okay, so we'll actually do an example of that in our presentation here, to estimate velocity. So it's not a true measurement, but it is an estimate, and it can be a pretty good estimate. For acceleration, we can use something called an accelerometer. So these are the types of motion that we may input. So as you can see, we're focusing in today on this fella right there, the rotary encoder. So what is an encoder? Well, in general, an encoder is a kind of a general concept. It's not just used for these things. So by way of example, this motor has an encoder on it. You can actually, this one has a little clear little window that you can actually look in there and see the encoder. Okay. This motor also has an encoder in it, but you can't see it. It's just kind of like in there. You can't really see the encoder. Here is a little encoder that's a mechanical encoder, uses switches, and so this is an example of one. So these are encoders. These are rotary encoders, but in general, an encoder basically takes something and it encodes the information. And so the implementation then depends on the application. So an encoder could be used for data compression. That is, instead of having a full set of data that's being transmitted, you might only transmit just the essential information that's needed to be transmitted, and that would be to reduce the full amount of data down to the compressed or the reduced amount of data. We need to do some data compression. The other is it can be used for information security. That is, if you are concerned about security of your data, you would want to encode it or encrypt it. So those are some applications of encoders. So what does the encoder encodes? Well, it needs to convert a change in position to a digital signal. Okay, so somehow it needs to do that conversion. And generally speaking, whenever you have any kind of input into a computer, you have an issue of what's called resolution. That is, how fine of a change in motion can you detect? Okay, that's the resolution. So the resolution depends upon the number of pulses in the specified distance. So, for example, you can have a motor with so this motor, for example, has an encoder with 44 pulses per revolution. That is, each time it goes around, it pulses 44 times. Okay. This encoder, this is actually an encoder from a high precision motion control device, and this particular one has 1,000 pulses per revolution. So that's even more precise. So that means for one full revolution, you get 1,000 pulses. So the distance in between each pulse is much smaller than the one that has 44 pulses per revolution. Okay, so the resolution depends on the number of pulses in a specified distance. So if you're only measuring in one direction, you will only need one channel. Okay, that is, you will only need one set of pulses to determine how far you've gone, and you just count the number of pulses, and the number of pulses you get will tell you how far you've actually rotated. So, for example, with this guy, if I turn it 1,000, if I turn it one full revolution, I should get 1,000 pulses. Okay, if I get, let's say, 500 pulses, that means I've only gone halfway around, right? So it's proportional that way. If you're measuring in both directions, it turns out you need more information than just one channel, because one channel alone won't tell you how far you've gone. Because remember, you can go fast, you can go slow with this thing. You go really slow, the pulses change really quickly. And this, if you're just using one channel, it has no way of knowing whether you're going forward or backwards. It has no way of knowing. Okay, so in order to know whether you're going forward or backwards, you actually need two channels to keep track of this. So often you will see channel A and channel B being used for the encoder. Sometimes you'll use have the I and Q, or what is called in phase and quadrature signals of the encoder. So those are the different types of information we may be using. Now, what generates the pulses? Well, there are a number of things that can be used to generate pulses. The first one is magnetic. Okay, so this is an example of a magnetic setup that has pulses. So these little fingers are either magnetic or they're iron, and next to it is a coil, like an electromagnet. And whenever one of these guys gets close to the electromagnet, there's a change in the voltage associated with that electromagnet, and so you can detect those changes. So the closeness to iron or closeness to a magnet will give a particular change in this magnetic pickup. And so when it's in between, when this thing is rotated so that it's in between fingers, you're going to get a different impression out here than you will when they're lined up. Okay, so that's what the magnetic does, and this particular encoder actually uses a magnetic one, so you can't actually tell because it's all embedded inside of here, but it actually uses a magnetic pickup. You can have pulses that are generated by switch contacts. So this little guy here, actually inside of there, it's actually a set of switches, and you can feel it. It has what are called detents. The detents, D-E-N-T-E-N-T-S, detents. The detents are fixed positions where it will stop. Okay, and so basically there are a set of switches that are connected here. And so depending on where the switches are positioned, you will get connection. So notice that this connection has 3 connectors associated with it. One is for ground, and then the other 2 are for phase A and phase B. Okay, and so this, when you use something like this, it has to also be connected up to power somewhere. The power is going to somehow come through these guys, and you probably need pull-up resistors and stuff like that. So, so there's additional circuitry required with these guys to be able to use them. This particular guy actually has another switch on there too. So there's another set of contacts back here for the switch. Okay, so that's another kind. So it uses switch contacts, and it's just as it goes around, it's actually switching, doing switchings. We can have optical, and there are 2 different kinds of optical pulses. Optical reflective, where you have a light source that comes and reflects, and so you'll have some kind of a disk in which you have dark spaces and light spaces, and if the light bounces off onto a detector, it can detect a difference between a light space and a dark space as it goes around. Okay, so that's what the optical reflective does. Optical transmissive means that the light actually has a light source, and then it has a photodetector, and in between is the disk, and so the light actually passes through instead of bouncing off. So those are a couple of different ways that the pulses can be generated. Now, when we talk about encoder, so we've talked a little bit now about encoders. That is, how do you get the information about the motion? And so we've seen that basically you have these mechanical situations that generate electrical pulses. So that's the encoder, that generation of pulses. Then we need something called a decoder to actually convert that set of pulses into something that's meaningful for us. For example, how many degrees have we gone? Have we gone a full revolution? Have we gone 90 degrees? That's the meaningful information we want to get, and we need a decoder to actually take the encoded data and make it meaningful. So for example, this guy here, as I said, has switches, and you can tell they're kind of like clicks. And so you could count how many clicks, for example. And so that would be the simple decoder is counting clicks. So that's the basic idea. But whenever you have an encoder, you also need a decoder. So this red guy over here is just showing that you have something that's kind of nebulous, from which an encoder gives you crisp information, and then the decoder is able to extract that information and make it useful for whatever purposes we're going to be working with. Okay, so that's the encoder and the decoder. Now, before talking about the incremental encoders, I want to talk first about absolute encoders. And I'm not going to say a whole lot about them, but I feel like it's important to say something about them. So first of all, absolute encoders are encoders where each position provides a unique code. Okay, so that's what the absolute encoder is. And they're often based on something called a gray code. A gray code is a code where the codes for adjacent positions differ by at most 1 bit. Okay, so if you go from one position to the next position, the change in the code is by 1 bit. So you may have 8 bits, but of all those 8 bits, also from one position to the next, 7 of them stay the same and 1 changes. Okay, so that's the way it's usually defined. So that's the basic idea of a gray code. When you use an absolute encoder, there is no data compression. And so in this case, it actually requires n channels. So if you have an n-bit absolute encoder, you're going to need n connections, at least n connections. You may need power, you may need ground, but you're going to need at least n connections. There's no compression done. So in general, because of that, it's more complicated to work with. But the important point of an absolute encoder is that you always know the exact position. Okay, you always know the exact position. There's no question about where it is. It is each position has a unique code associated with it. So you read that code, you know exactly what the position is. Okay, so here's an example of a wheel that can be used in an absolute encoder. So this is an 8-bit absolute encoder disk. So each ring basically corresponds to a different bit. Okay, so you can imagine there being eight readers, transmitters and receivers. Okay, and each one of those is getting a bit on there. And so in this particular case, the number of pulses per revolution is 2 to the 8, or 256 pulses per revolution. Again, this requires 8 signals, 8 channels to keep track of. And in this case, you only get what is called 1x decoding. That is, you only know for each time when you read. So let's suppose your thing is lined up here. You're going to read a certain set of values. Okay, so this is out here. These values at the outermost are the least significant bits. The innermost are the most significant bits. So if I were reading along here, I would get 1, 1, 1, 0, 1, 1, 1, and then here I would get 0. Okay, so that would be the values that are read. Okay, so and if this thing rotates and a bit changes, I know that I've gone a distance of this 360 degrees divided by this number. That's the distance I've gone. I don't get any additional resolution from this. Okay, so that's what 1x decoding means. We'll talk more about 1x decoding, 2x decoding, and 4x decoding when we get to the incremental encoders. So the value of this is you always know where you are. In particular, you know where you are at startup. That's really, for some applications, that's really important. For some applications, it really doesn't matter. But some applications, it's really helpful to know exactly where you are at all times. Or at least at some point, you know exactly where you are. Gray code decoding is used. So that's the most common form of absolute encoder. So that's the absolute encoder. It is very useful for certain applications. But again, you don't get any data compression. Now for the incremental encoder, we can have single direction or unidirectional encoding and decoding. So what does the unidirectional or single direction encoding look like? Well, so we will often have something like this. We'll have a disk, okay, a disk with an emitter, a light emitter, and a detector. And the disk, in this case, this shows a transmissive optical encoder. Okay, and so you can see that the emitter emits over to the detector, and you can see that if the disk has a slot that happens to line up with the beam, then the light will go through. Otherwise, if you don't get a slot that lines up, the light will be blocked, and you won't get anything going to the detector. So it's pretty straightforward. Here is an example of a system that has. This is actually taken from an old printer, and you can see that here's the disk. It has slots in it. It may be hard to see those slots, so maybe you can see them. But anyway, as this thing rotates, here's the emitter and detector that are associated with that, and so you can see how it would be set up. So that's an example of one that uses single direction encoding. And so basically what happens as you rotate this disk, or the whole shaft with the disk on it, we get pulses. Okay. Now the pulses out of the detector are never actually this clean. Usually what happens is the signal that comes from the detector goes through a little bit of circuitry to square up the wave. So in general, so that you get a nice square wave with a 50% duty cycle. So that's the way it's usually set up. So there's some circuitry in there that kind of helps to balance the thing out so that you get a nice 50% duty cycle. Okay, but that's basically what you get. As this thing rotates, you get pulses. Okay, you get pulses. So theta here is the angle of rotation. It's very common to use the Greek letter theta. So if that symbol is throwing you off, don't let it shake you. It's just a Greek letter theta, and it's often used to represent angles. So in general, this disk may have a number of slots. The number of slots corresponds to the number of pulses per revolution. Sometimes you'll see this abbreviation PPR, pulses per revolution. So in this case, we're going to assume we have n pulses per revolution. So we can have, from that, when we do the decoding, we can either have 1x decoding, in which case the resolution is 360 degrees divided by n, or we can get 2x decoding, in which case the resolution is 180 degrees divided by n. So notice when it comes to resolution, the smaller the number, the more accurate you're able to read. In other words, you're able to detect a smaller change in the motion. And so that's what the resolution is. So you can see how the 1x would be, the 1x, for example, would check every rising edge of this thing. Every rising edge basically corresponds to every pulse. And so you get, for every pulse, you get one rising edge. Okay, and so that would give you 1x resolution. To get 2x resolution, you would actually check both the rising edge and the falling edge. Okay, and so each pulse, you actually get 2 transitions. Okay, so that's why you get 2x resolution. And so the distance that you travel is half the distance that you travel when you use a full pulse. Okay, does that make sense? 2x. Okay, so that's the 1x and the 2x decoding. Okay, so that's an important thing to keep in mind. So when it comes to decoding now for single direction, again, we can either count pulses, that gives us 1x decoding, or we can count transitions, that gives us 2x decoding. And so the counting can either be done by polling the channel or by using the channel to trigger interrupts. Okay, so these are 2 options that we can get: polling the channel or using the channel to trigger interrupts. So this is helpful. And that's basically how simple it is to keep track of. So remember, polling is where your loop program basically continually remember, it's continually looping, and basically polling would be each time through the loop, it checks to see if there has been a change in that signal. If there has been a change, then we would, or in particular a rising edge, then we would do the 1x encoding. We would update a counter that counts the number of pulses. And so, the number of pulses then, if you multiply that by the resolution, you get the total distance that you actually traveled. So in general, we need a counter. And so we can count the pulses or count the transitions. So we need a counter. And so generally, we want to use a long counter so that we can get a lot of revolutions, a lot of turns. Okay. And so it's often common to use an unsigned long variable for the counter, or if we use the standard int definition, it would be a uint32t. Okay, so it's recommended that you use a counter like this for the counter. So what that means is it can have many turns. It can count many times before the counter rolls over. Okay, so when you roll over, it's like your position has increased, and then suddenly it drops down to 0. Okay, not so good. Okay, because we know it's not 0. It's actually some large number. It's gone a large number of pulses, and so it's helpful to have a long counter for use with this. So that's simple. We have the two methods, the polling and the interrupt. So let's take a look at the code for each type of decoding for this 1x. Sorry. Here we go. So let's take a look at the code. I didn't put any comments in there. I'm going to comment them as I go along. So unsigned long count. Then I also defined unsigned long some time variables. And so for this program, all this program is going to do is it's going to keep track of the count, and every so often it's going to display the value. Okay, it's going to display the value. And then I have this variable a and AP. So a and a passed, and that's a byte, and we'll talk about where that's going to be used in a little bit. So in our program, we first set up the serial monitor to be able to display things on the console, and then we're going to connect channel A pin 3. Okay, so we're going to use that as our input for this problem. Okay, so input mode. We're going to set the initial time. Now, in our case, this program is going to be using an optical encoder, and as an optical encoder, the optical encoder doesn't need a pull-up resistor. Okay, so if you use a encoder like this, which incidentally, these are often called digital pots, digital potentiometer. Okay? It's not really a potentiometer, it's an encoder, but it's often referred to as a digital potentiometer. And these little knobs are really handy because you can use them to like flip through menus and all, move pointers and stuff like that. So those guys are really handy. Okay, so the single channel is coming into digital input 3. Then we establish the initial time, and we establish the initial value of our input. Here I've set this up as a byte. You could also set this up as a Boolean, because when you do the digital read, it's going to read it in as a Boolean. Now, as a Boolean, it's actually stored as a byte, so you can do either way. They work the same. So here's our setup routine. Here's our loop routine. So in our loop, I'm going to read digital input 3, and I'm going to do an exclusive OR with the past value of A. So this gives me A, and I'm going to do an exclusive OR with the past value. And what that does is it checks to see if there's a difference between A and the past value of A. Okay, so if there's a difference, that means there was a transition. Okay, so this is checking transitions. This is doing 2x decoding, which in general you want to use as high a resolution as you can. That's generally a good idea, unless you do have the issue of your counter overflowing too often. Then you want, and if you don't need that much resolution, then it's okay to use a lower resolution, 1x for example. So here I'm using 2x, and in which case I'm only checking to see if there's a difference. I'm not checking to see if it's a low to high transition. Okay, so that would be different logic that would be used for that. Okay, so if there's a difference, the exclusive OR would say so. So if there's a difference, then I want to increment the counter. Okay, then I'm going to replace the past value of A with A, and then I'm going to go through here. I'm going to take the current value of microseconds, and I'm going to subtract the past value of time. So basically, this is computing the elapsed time. So E time here stands for elapsed time. How much time has it been since since I reset the timer? Okay, so if the elapsed time is, so notice this basically is 1 million microseconds. So that's basically every 1 second. If the elapsed time is 1 second, then I'm going to print the count. And when that happens, I'm also going to update my counter, my timer, so that the present time is the past time in this elapsed time. So every second I'm going to reset my timer. Okay, and so that's what this is doing. Okay, so this is a polling routine. So basically in my loop, I'm always going to be doing this. I'm always going to be checking to see if there's a difference between A and the past value of A. Okay, and so this is one way we can do the 2x decoding using polling. Now polling has its definite limitations. That is, it really depends on this loop being very fast. If it's not fast, it's possible that A could change twice and you wouldn't know it. So in other words, you've skipped some counts, and so that's not a good plan. Okay, so and especially you can miss a transition if you're in the process of printing, which it's not slow, but it's relatively slow compared to everything else that's going on in the loop. So it's during this time you could actually be missing counts. So polling definitely has its limitations. So we move on to use interrupts. Now, I'm going to keep it simple in terms of interrupts. That is, I'm only going to use interrupts that are the standard external interrupts that are available through the Arduino IDE. Okay, we'll get into the pin change interrupts and other things in the next presentation. But for now, we'll keep it simple. So again, unsigned long. We're going to keep that count as an unsigned long. I'm also going to keep track of time like with the other way. So this basically does the same thing as the previous program. It uses interrupts though. Okay, so again, set up my serial monitor. Again, I connect my input to digital pin 3, which incidentally, digital pin 3 is attached to external interrupt 1. Okay, external interrupt 1. So that's one of the reasons for using that pin. So if that pin's not available, then you can't use, if either pins 2 or 3 are not available, you cannot use the standard external interrupts. You have to use a pin change interrupt. So in this case, our whole system is simple so that we don't have a lot of stuff going on. That pin is available. So attach interrupt is the next line, and this is actually the name of the interrupt service routine. Okay, so here's the interrupt service routine it's going to call. And I'm going to use a pin change interrupt here. So it's a change interrupt. So this uses the standard interrupt setup. And then again, I set up my time to be, so I initialize my timer here. So notice here, I don't have to keep track of A and A passed. The interrupts will automatically, whenever there's a transition, it's going to go to this interrupt service routine. In this case, all the interrupt service routine does is increment the counter. That's all it does. Okay, so now in my loop program, this is what I have in my loop program. Notice I don't have to check to see whether it transitioned. Okay, this keeps track of its transitions, and so all this does is it keeps track of when the elapsed time is 1 second, and it prints out the value when the elapsed time is 1 second, and then it resets the timer. Okay, so you can see in some ways this is actually a much more streamlined, and it's actually a much more robust approach to using the encoder. Okay, so we've shown both methods, polling and using interrupts. So I definitely recommend using interrupts. Now, as I mentioned, one of the things that the encoder can also be used to do is to estimate velocity. So velocity is the speed. How fast is that thing rotating? So when you think of speed, you need to think distance over the amount of time it took to cover that distance. Okay, distance over time. So if you're thinking calculus, it's it's the derivative of the position with respect to time. But we don't need to talk calculus here. We can just keep it simple. The velocity is the rate. So you look at the distance divided by the amount of time required to cover that distance. So if we can have a standard time that we use to keep track of that distance, and in this particular code, I'm going to use 1 second. So I want to check the velocity every second to see. I could use a smaller time if I wanted, but 1 second's a good thing, especially if you're going to display it on the console. Anything faster, it goes too fast. It may be going too fast. So anyway, this is a good way to do velocity estimation. So basically, here I'm going to use interrupts, and notice I use the exact same interrupt service routine for this. All of this is exactly the same for the setup. The only difference now is that I increment the count. Okay, I'm sorry, I reset the counter each second. Okay, and so basically the velocity then is how many pulses did I count in 1 second. And so in this case, the velocity is actually pulses per second. Okay, so and it's like, well, why is that velocity? Well, we'll talk a little bit about units here in just a little bit. But in this case, how many pulses did I get in 1 second? So after 1 second, I reset the number of pulses, and so basically I'm counting pulses, which basically is looking at distance. But then it's not concerned so much with the actual distance; it's concerned with how far I've gone in a certain amount of time. And so that's one of the differences here. So the count, the thing that's being printed out in the serial monitor then is actually it's the number of pulses per second, okay, or rather the number of transitions per second. Okay, so that's actually what's getting printed out here. And I could show you what the Arduino, this actually does compile, and it runs, and it does exactly what you would expect it to do. So I'm not going to show you what the Arduino actually looks like when you do this, because it's pretty boring. I mean, it just does what it's asking in every second. So in this particular case, if you're not turning the encoder, what's going to happen is it's going to go to zero velocity. It's going to go a whole second. It's not going to count any pulses. It's going to give you 0 velocity. Otherwise, it'll count the pulses and tell you how many pulses occurred in that second. Okay, so, well, as I mentioned, units are important. In general, for real systems, units are essential information. Okay, they're essential information. For a real system, for example, in a car, velocity is you want it to be miles per hour. That's the most common thing we use in America. If you're in other countries, it would be kilometers per hour. Pretty much any other country, it's kilometers per hour. But in America, it's miles per hour. But those units are essential to know what the significance of what you're doing is. And so the units need to relate to what the relevant quantity is. Okay, so the encoders have a fixed construction. In other words, if you have a linear encoder, you're going to have pulses per inch or pulses per millimeter. If you have a rotary, generally it's going to be given in pulses per revolution. But so even though it's given in pulses per revolution, we may not want the information to be given back to us in terms of revolutions. We may want to have it in terms of another unit like degrees. Okay, so here's an example. We have a rotary encoder on a motor shaft with 512 pulses per revolution. Okay, so this particular motor right here actually has that. Okay, so it's kind of a hefty motor that we got here, and this one has those encoder wires, 512 pulses per revolution. Okay, and so since one revolution is 360 degrees, then for one X decoding, each count means the motor has turned 360 divided by 512, so that's how many pulses per revolution. 360 degrees per revolution, 512 counts per revolution, and so each count means it has rotated by 0.7 degrees. For 2x decoding, then in a sense, each revolution, we have 512 times 2 transitions. That gives us 1024 transitions per revolution. So when you divide 360 by that, we get 0.35 degrees. So notice in this case, each time we get a pulse or a rising edge, that means we've gone 0.7 degrees. Here, each time we get a transition, that means we've gone 0.35 degrees. So we've gone at a smaller distance, and so that's a finer resolution, and that means we're more accurate in terms of the motion. Okay, so units are important. Okay, we've talked about one direction, unidirectional, single direction encoding and decoding. Now we're going to talk about bidirectional encoding or decoding. There are a number of ways that this bidirectional encoding or decoding can happen. This is probably the most common way, or a very common way to do this, is to have detectors set up adjacent to one another. Okay, and in this case, again, we have a transmissive disk. And so here we can see that, notice that this one, the beam is able to go through because of the way it's lined up. This one, the beam is being blocked because of the way it's set up. And so what happens then is you actually get two channels, okay, and you get pulses. Okay, and so you have two channels. One is called the in-phase channel, the other is called the quadrature channel. Okay, so phase A and phase B. So sometimes you'll see them as the A and B or I and Q. So different ways you'll see them referred. And basically, as you go along, you get pulses, and the two sets of pulses are out of phase with one another. They're not aligned. Okay, they're intentionally out of phase, and that out of phase allows us to have information about whether we're going forwards or backwards. Okay, so how does that work? Well, first let's take a look at a little video that illustrates this encoding. Okay, so here we have I'm not showing the emitter or the detector. What I'm showing is the beam. Okay, and so you can see that when the beam lines up with a hole, it goes through it, and otherwise it's blocked by the disk. Another thing that this illustrates is something called an index. Okay, so some incremental encoders have an index slot that can be used to keep track of where the zero position is, so you know exactly where the zero position is. And so once it lines up and you get that basically this bit being set. So now notice there's 3 channels. It requires 3 channels, and so in general, when you have a 3-channel encoder, you have A, B, and Z. Z is sometimes called the index channel. It's not very common to have that, but it is available in some situations. Okay, so that requires additional logic to keep track of what happens when you pass that index Okay, so this allows you to see how sometimes you have both. You can have both channels being transmitted. Sometimes you can have both channels being blocked. Okay, and so forth. Okay, so this just kind of illustrates that whole process of the encoding for bidirectional signals. Okay, so when we look closer now at these bidirectional signals, as I mentioned, we have this whole these two channels, and these two signals are out of phase with one another. Okay, so each of these channels has the same number of pulses per revolution, and if we wanted to use single channel, we could just ignore one of the channels. We could use one of the channels and ignore the other channel, and we could get back and use the single channel decoding. Okay, but again, for single channel decoding, you can only be going in one direction, only in the positive direction. So, for example, this printer thing is designed so that the paper only goes one way, right? And so that's what these rollers with the little rubber thingies on them are for the paper, and it's only the paper's only designed to go one way through the machine, and so that's what that's all about. Okay, and so in some applications, one directional encoder is fine. For many applications, though, you want to know whether you're going backwards or forwards, and so that's important. So, for example, with this little guy, you want to know, am I going right or am I going left? Okay, and so you want to be able to keep track of that. Okay, so this encoding actually gives us the information as to whether we're going forward or backwards. So how do we get that information from this? Well, first of all, first thing we do is we look at the transitions. Okay, the transitions that occur. So notice that the transitions are equally spaced. Okay, the way it's set up, you get equally spaced transitions. So the blue lines indicate the transitions when either A or B is transitioning. Okay, so you can see that if you look at the combination of those two transitions, that all the transitions are equally spaced. That's the way it's set up. Okay, and we can now look at the value of A and B at each of those places. So here, notice that A is 1, B is 1. Here, A is 1, B is 0, A is 0, B is 0, A is 0, B is 1, and then the whole thing repeats again. So you have 4 possible combinations, right? 4 states. 4 states. And we can actually give those states names. So here is one set of names you can pick. You can pick other names. You could call it Fred and Ralph and George and Susie. Although I don't know why you'd want to do that. But anyway, you could. Anyway, we just call it, we give them names. 1, 2, 3, 4. And sometimes we can choose a name that makes it convenient to work with things in other ways. Sometimes not so convenient. So we're going to start here with these names. Okay, so state 1 always refers to the case when both A and B are 1. So notice here's a state 1 here. Here's a state 1 here. Notice that over here is actually a state 1, even though I haven't actually written down in there. And then state 2 is when I have 1 and 0. State 3, 0, 0. State 4, 0, 1. Okay, and so notice that state 1 is always next to state 2. Okay, it's always next to state 2 and always next to state 4. Okay, state 3 is always next to state 2 and state 4. State 2 is always next to state 1 and state 3, and so forth. Okay, so we always have that. So we have this situation. We can define the states. So again, the states, state 1 is when A is 1, B is 1. State 2 is A is 2, A is 1, B is 0, 0, 0, 0, 1. So I have those 4 possible states. Okay, so now how do we use this information to detect whether we're going forward or backwards? So notice that this is showing what happens to the pulses as we rotate. So theta here again is the angle. So this is showing the angle. So at this particular, at some particular angle, we would get some combination of A and B. Okay, depending on the angle. Okay, so notice if we're, for example, at this state here, 0, 0, state 3, and we get a transition occurring. Well, the fact that we have a transition doesn't necessarily itself tell us whether we've gone forward or backwards. So then the question is, what do we have after the transition? So here we had 0, 0. What if after the transition we had 1, 0? Well, that means here's 1, 0. That means we have gone backwards. Okay, so that indicates that we've gone in the opposite direction. So that's positive direction. So we've gone in the negative direction. So we need to keep track of the fact that we've now gone backwards. Okay, or we've gone in the negative direction. Okay, and so if we were at 0, 0 and we got 0, 1, then we would know we have gone in the positive direction. And so for each state, you can determine based on what the previous state was, whether you've gone forward or backwards. Okay, so based on what the previous state was. Now, if you're just seeing, for example, on an oscilloscope, what the things are doing, this is the kind of thing that you would be looking at. Notice now this axis is not angle, this is time. So this is what happens as it changes in time. We have A and B. And notice that if you're going forward, then B switches before A in time. So for example, here, I'm having a downward transition. This downward transition occurs before this downward transition. And so that would tell us that we're going in the forward direction. In the reverse direction, okay, A downward transition occurs before B downward transition. And so it's just the opposite. So that's how we would keep track of, that's how the encoding is set up. Okay, well, let's get specific now. Let's talk about 1x decoding. So now we've got a set of signals and we want to decode. Well, we have all this information. In order to do decoding, actually we end up throwing away a lot of information. Okay, because again, we only want to check one. We want to check what's happening each time the pulse changes. So we set it up basically so that when B is 1, we're going to look at the transitions of A. Okay, so we're going to focus on that transition. So when B is 1, what's happening with A? A is either 0 or 1. Okay. A is either 0 or 1. So if B is 1 and A is 1, and then A changes to 0, that means we've gone backwards. If A was 0 and it changes to 1, we've gone forwards. So if I detect a transition, that means it has changed. So if I detect a transition and the next value of A is 0, that means we've gone backwards. Okay, we've gone backwards. Backwards. If we detect a transition and the next value is 1, that means we've gone forward. Okay, so that's a helpful way of being able to check this. Alternately, you can do it this way. If I have a rising edge on A, so remember when B is 1, okay, and I get a rising edge on A, then I want to increment my counter. So remember the counter, just like we had with one directional decoding, bidirectional decoding, we would have an increment as well. But notice if A is falling, we're going to decrement our counter. Okay, so that's the difference with bidirectional decoding, is that we can decrement, not just increment, we can also decrement. Okay, so that's one way of keeping track of that decoding. Okay, so that's the 1x decoding. Notice that we're only using one pulse per revolution when we, one transition of the entire pulse. So we actually have a lot of information we're not using. We're not using any of this information over here, so this is a coarse way of keeping track of the position. 1x decoding. Now for 2x decoding, we're going to be looking at whenever A transitions, and whenever A transitions, then B is constant during that transition. So here it's constant, here it's constant, And so we would basically have this as our transition map. So when B is 0, if A is rising, so here's B is 0, A rising means we're going that direction, so we decrement the counter. And the opposite is when A is falling, okay, then we increment the counter because we're going in the positive direction. Likewise, when B is 1 and A is falling, that means we're going this direction. Okay, we're going back. That's we're going to decrement our counter. Otherwise, if it's rising, that we're going to increment our counter. So this is how we would do the 2x decoding. Now we can do a 4x decoding. And this is actually probably the most common form using an incremental encoder, is the 4x encoding, for two reasons. One is it gives the finest resolution, and second is it uses all the information available to us. It doesn't just use, it isn't just looking at when A transitions. Okay, it looks at all the transitions. Okay, so in keeping track of that, now we have 4 states to keep track of, not just A. We have 4 states. So we have a prior state. Remember, we call those 1, 2, 3, and 4, and we have the present state 1, 2, 3, and 4. Okay, so if the present state was 1 and the prior state was 1 and we had a transition, how can you get a transition and stay at the same state? You can't. That's why there are x's here, and it's the same here. 2 can't stay at 2 if you go through a transition. 3 can't stay at 3. Okay, 4 can't stay at 4, and so forth. Okay, so that's why we have these x's along the diagonal here, because that can't happen. These x's happen because you can't jump from state 1 to state 3. You have to go through state 2. Okay? Similarly, you can't go from state 2 to state 4 directly. You can't go from state 1 to state 3, state 2 to state 4. Okay, so that's why we have those x's there. Okay? So the present state, in this case, is 1. The prior state was 2. Okay, so if the prior state was 2 and the present state is 1, that means we've gone backwards, and so we decrement. If the present state is 1 and the prior state was 4, okay, so in this case I have 1 and the prior state was 4, we've gone from 4 to 1, we've gone in the positive direction, we're going to increment our counter. And so this map basically shows all the things to do at each transition. Each time a transition occurs, we're going to update our counter or not, depending on what the x is. In general, the x means do nothing. Okay, we're going to do nothing. We're not going to. So supposedly that can't happen, right? Supposedly you can't get a transition and be back at the original state. Okay, but if it did, we would do nothing because we wouldn't know to increment or decrement. So the safe thing to do is do nothing. Similarly, I can't jump from state 1 to state 3, and so if that happens, then I'm going to do nothing because I don't know whether it went forward to get there or if it went backwards to get there. Okay, so that's the thing to do. Do nothing. Okay, so this is basically what's happened. So basically here, AB is 1, 1 in that state. AB is 1, 0, 0, 0, 0, 1. And so again, these are just the definitions of the state. Okay, so now in terms of code, how would we implement a complicated setup like this? This is fairly complicated. How would we implement a complicated thing like that? Well, it's like any programming, there are a number of constructs that can be used to do that kind of thing. So we can use the switch case methodology. We can use if, else, 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 else kind of thing. We can use an array, and we can use pin positions. Okay, I'm going to use pin positions later when I come to talk about the pin change interrupts. Okay, so here's how we would code that problem using the switch case methodology. So again, we would define our count to be long. We would again set up our time variables like we did before. Here I'm going to have now the inputs A and B, and I'm going to go ahead and call those Boolean. just for fun. I'm also going to keep track of the state and the past value of the state. Okay, so state is values 1, 2, 3, and 4. All right. In my setup routine, now I'm going to start up the serial monitor, and I'm going to define pins 2 and 3, which are our external interrupt pins, so channel A and channel B. And I'm going to define these interrupts as change interrupts, and I'm going to have A change and B change. So I'm going to have 2 interrupt service routines based on these 2 interrupts. Okay, and I'm going to initialize my time. I'm going to read the initial values of A and B, and based on those initial values, I'm going to determine the state, the past value of the state. Okay, so this is how I'm going to determine the past value of the state. Okay, in my loop program, notice my loop program is very simple. It's just like this loop program I had in the one directional situation, where I'm just printing out the count every 1 second. Okay, the rest happens in the interrupt service routine. Okay, and actually there are 2 interrupt service routines, but it turns out they're identical. The only difference is the name. Okay, they're identical. They do exactly the same thing. So that's makes it easier. So once we get one working, we just do the other. So here's so notice bidirectional 4x decoding. So that's what that BD4x is all about. All right. Now here's the routine that we get. Okay, and remember I said we're going to use switch and case. So here's what we do in the interrupt service routine. When the interrupt service routine is called, we first read A and B, okay, and from that determine the present value of the state. Okay, and based on that present value of the state, I'm going to do my switching. Okay, so switch based on the state. So in case 1, that is in state 1, I check if the past state is 2, I'm going to decrement. If the past state was 4, I'm going to increment. Okay, so again, that's just implementing that table. That's actually the first row in that table. Okay, and then break. Case 2, I check to see if my previous state was 1 or 3, in which case I'm going to increment or decrement. So notice if the past was 2 or 4, I'm not going to do anything because supposedly that can't happen. So basically I'm not doing anything in those cases. So I just leave that out. Case 3, simplify it. It checks to see if I was previously at 2 or at 4. Again, if I was at 4, that means I've gone backwards. If it was at 2, I've gone forwards. And so the count is incremented or decremented appropriately. And then this last one is actually, I can use either case 4 or default. I choose to use default, and in which case I get this, because I can only have 4 values possible for the state. And then I reset the past value of the state here. And so that's all that the interrupt service routine does. And again, the B change interrupt service routine is exactly the same as the A change interrupt service routine. You can plug this code in and it'll work. Okay, and it'll actually keep track of the counts. And I could show you, but it's kind of boring to look at. So, but one of the things that's important when you do this, if you turn it to a certain point, and you stop, it'll stay at that value. Okay, it won't go back to 0, not like the velocity. Okay, so if you move it forward, it'll go forward. If you go backwards, it'll actually go, and it can actually give you a negative number and so forth. Okay, it'll increment, it'll decrement. So that's basically what that's doing. So that is the switch case methodology for implementing that table. And the array method is another method of implementing that. Another method is using if and else, but basically you can do if you can do it with a case and switch, you can do it with if and else. It's basically the same kind of thing. So I'll skip that one. The array is an interesting way of doing things because it is a way of keeping track of the all of the transitions. Okay, so here's our transition map. Notice that I've now changed the state names. Ooh. I've changed them to be 0 through 3. Okay, so it's everything is exactly the same, but instead of going through 1 to 4, you're going 0 through 3. And it turns out by doing it that way, there's a clever way that we can use this to work with an array. Okay, and so we define this quadrature encoder matrix or array, QEM. It's going to have 16 values. So that's the 16 values. Okay, and so basically I just read them off in a row. And basically each row gets stacked side by side. All the rows, wherever I see an X, I put into 0. Wherever I see a decrement, I put in a -1. Okay, and whenever I see an increment, I put in a +1. Okay, so I have this row, which is these first 4 values. The next row is, again, 1, 0, -1, and 0, and so forth. So I put them all into this matrix. So if I have this particular situation, for example, my present state is 2, my previous state was 1. I can access that using this formula. The index for this element in this array is given by this. 4 times the state. Now, why 4? It's because we have 4 columns here. That is, each row has 4 elements in it. So 4 times the state plus the past value of the state. Okay, so this 4 times the state, so 4 times this picks off which row. Okay, so this picks off the row, this picks off the element in that row. Okay, and so the combination then can be used to uniquely address every single element in this array. Cool, huh? And so I do index, and I do this calculation. That gives me the index value, and now I update the count with whatever element is in the index at that point. Okay, so this will either increment, decrement, or do nothing. Okay, so that's simple. I don't have any ifs and elses and switches and all that kind of stuff. So to me it's very elegant, but it does take a little understanding of getting it through your head exactly what this index is doing and how to access the elements of this array. Okay, so clever. I didn't invent this. I found this. Someone had it on the internet, so it was a clever way, and I just picked it up. And I don't even remember who did it, but it was clever. So if you're the one who did this, kudos to you. All right, so how would we actually implement that in code? Okay, notice that in this case, again, the change, everything else for the code would be the same as we had before with the switch case. Now what we change is the interrupt service routines. And so notice these 2 interrupt service routines are basically the same thing. Well, exactly the same thing. So again, we read A and B. We determine the state based on A and B. Notice that I've changed the values here. Then we compute the index. And based on the index, then we would access my array. And then we would update the state value. Okay. And so that's how we keep track of the past value of the state, okay, which is used here. And then the B array is the same. So this allows us now to be able to do bidirectional decoding. And it works. You can take this code, plug it right in. The only thing that's missing from this code here is that actually I need to have define this right up front as a global variable. Actually, probably as a volatile. I need to declare it as a volatile. A volatile is used in a interrupt service routine if you don't declare it as a volatile, because the interrupt service routine isn't called. It's not called by either the setup program or the since it's not called by the setup routine or the loop program. It's not called. Sometimes the compilers will not allocate memory for those variables because it says, oh, we don't ever use those variables, so we're not going to allocate space for them. And so that's why you have to use the volatile declaration, because otherwise the optimizer tries to optimize time and space on the microprocessor, and it'll optimize some of those things away, and you don't want it to do that. So that's why you have to use volatile declarations. So this is the quadrature decoding, 4x quadrature decoding. So we've gone through 1x decoding, 2x decoding, and now 4x decoding in a very standard way. And if all you do is watch this lecture, you've got a lot going for you. In the next lecture, we're going to look at how to work with this in a little more general terms and in more optimal terms. Thanks for watching.